What's that? Yeah, you were leaving, right? Or something. Yeah, we can work something out. If you wanted to do it, are you saying this Thursday, or you still want to do it because you're not going to be here next week?
Yes, sir.
Yeah, we can work something out. Yeah. Okay. Did you have a good weekend?
Yep.
Easter. Shouldn't Monday be a holiday? Easter Monday.
I think Tech had it all.
Yeah, there were a couple of schools that were off. Okay, we have a lot of little announcements here. Obviously you can read, but I will just go through these. We had an exam scheduled for this Thursday. We're going to move it to Tuesday. Any objections? Any major objections to that?
Nope.
Okay, good. Now, we have to have it next week because next week is also the drop date. So if you're concerned at all about your grade in this class and you're at a point where you're like, you know what, I think it's better, if I retake the class because I don't want a C, I want to get an A, or whatever. You have till Friday to drop. Make sure you go through ACES, which is the same place you register for a class, and that's where you would drop the class. And this goes for this class and any other class that you might be taking. Make sure that you go through that. If you cannot figure out how to drop a class, the best thing to do is email your instructor. Just let them know, and that way it's officially documented that you want it to be dropped, and usually they can drop you, even if it's after the date. So, all right, grades. So I've fallen behind on grading. Yeah, it happens. So I'm behind. I have all this stuff here for your class. I plan on going through that this week and updating everything on Canvas. And that way you really will know next week. You'll take your test on Tuesday. I will have it graded and returned to you by Thursday. Yes. And that way you know whether or not you want to drop that next day on Friday. So you should have a real good idea of where you are before that drop date. Understand? Okay. And then let's see. Today we're going to continue related rates, but we're going to do problems that are more business-oriented problems. And then on Thursday is going to be nothing but review. This test we're going to be taking next week is actually only over a few topics. It's derivatives of exponential and logarithms, implicit differentiation, and related rates. And that's all that's on the test. So it's a narrow set of topics. So I don't anticipate that the test is going to be super long. The word problems we do today are going to be really important, okay, because you'll see these on the test. Any questions or concerns or anything about any of this before we get going? Okay. All right, let's get started. So remember last class we were doing that ladder problem? Yes? Okay, so the ladder problem, I could tell when I was going through it, some of you were slightly confused, and that's okay, because the problems we were doing there were more like what you would see in a traditional calculus class. There's a lot of physical examples where this is moving and that's moving. What we're going to be looking at is something that's going to look more familiar: cost functions, profit functions, revenue functions, and trying to figure out how those quantities relate to one another. So let me just remind you about implicit differentiation. So remember, I'm just going to put implicit diff. Everyone understands I'm saying differentiation there. So if I put an equation up on the board here, let me put something up here. If I write cost is equal to 2x squared plus 500, okay, that's like a cost function, all right, cost equation. Then I could ask us to take the derivative of this, and I need to tell you with respect to what variable. And that's something that in implicit differentiation related rates is kind of a new idea, is that I need to tell you to take the derivative with respect to, and this is what I mean, I need to tell you what variable we're going to differentiate with respect to. So for example, I could say here, take this equation and take the derivative with respect to x. That means I would treat x like the variable, right? The what we call independent variable, but c is another variable, right? But we will differentiate with respect to x. So let's do the derivative of this with respect to x just to make sure we all understand what would happen, all right? So what would happen if we take derivative of that with respect to x? On the left-hand side, I could write like this. This means take the derivative with respect to x of the left side c equals the derivative with respect to x of the right-hand side. So this is slightly different notation than what we saw before. Does that look a little different? Okay. This is just letting everyone know we're taking derivative and we're treating x like our variable. So what is the derivative of c with respect to x? This is the part I think was confusing people. Maybe we should start on this side? Okay, let's start on this side. What is the derivative of 2x squared with respect to x? So that means we're just going to take the derivative the way we normally did. So what is the derivative of 2x squared? 4x. So the 2 comes down, becomes 4x, right? So there's nothing new here. This is 4x. And then plus, what's the derivative of 500? 0, because it's a constant, right? So that side is just what we normally expect to see as a derivative. That clear? But the left side is not, I guess, what we're used to seeing. What is the derivative of c with respect to x? dc over dx. Okay, that is the derivative. Now let's try and understand what this is saying. It's saying that when we differentiate with respect to x, we're saying, look, if we change x a little bit, right? So like x, let's say x, this is our cost. Let's say x is the number of employees we have, okay? So if we change the number of employees, this equation tells us how much our cost changes. So this is telling us the change in cost with respect to the change in x, the change in employees. Does that make sense? So you change your employees, your costs are going to change. And this equation tells us exactly what that relationship is. Questions on that? You're okay with this? Okay, let's try something else. What if I do the same equation, but I say take the derivative with respect to c instead of with respect to x? So this will be the derivative with respect to c of c equals the derivative with respect to c of 2x squared plus 500. So I'm doing it on both sides again. This time, c is the thing we're changing. If I change my cost a little bit, then how does everything else change? That's the question. So what is the derivative of c with respect to c? 1. This time it's 1. Right? Y'all need to let me know if this makes sense or not, because I'm getting looks like this. So does that mean you get it or not? Look, the derivative with respect to x of x is 1. Okay? The derivative with respect to x of c is not 1. That is dc dx, right? So if the variable down here is the same as the variable here, then you would get 1, right? So this would be what? 1 over here? Equals, now this is the tricky part. This is the really tricky part. We're taking the derivative with respect to c of this. So what is the derivative of 2x squared with respect to c? Close, close. We're going to take derivative of this. What would you think the derivative of this is? 4x, right? 4x. But, let me write it down over here. We have 2x squared. So what you did is you said power rule. You're going to bring the 2 out, right? That's going to become 4. And then x to what power? First power. And then the chain rule says now you go in and take the derivative of what's in here. right? The base. What is the derivative of x with respect to c? dx over dc. dx dc. So the derivative of this is actually 4x dx dc. So it's almost, see, it's almost this, but you have that additional dx dc here that's not here. What about the derivative of 500? 0? So this is it right here. This is the equation after implicit differentiation. I really get this sense that y'all do not understand what I'm doing. Let me.
It's just like doing y, just different variable.
Yeah. Ask a question. I mean, this is your time. You have a test in a week, so. Do you have another way of explaining it? That.
Question.
Yes.
So, like, for the first one.
This one right here.
No.
No. Oh, this one up here.
Yeah.
Yes.
So, why would you put a 0? Like, do you have to put a 0?
Oh, no. The zero's not there. I just want to make sure everyone understands that, like, the derivative of a constant is 0. At the end of the day, that's not there. And then over here, it's not there. Okay, I just want to make sure everyone understands what happened to the 500. Anything else? Let me ask you another one. Same equation, ready? What's the derivative with respect to t? Well, t's not even in here, is it? Right? So the variable I'm differentiating with respect to does not even appear in the equation. Right? So it's like if we let t change a little bit, how much does this stuff change? That's what we're asking. And what's that? Well, the thing is, when we do this, will the derivative of any of these ever be 1? No. They won't, because the variable that appears down here is not ever going to appear up here. So we will never have the derivative of one of these turn into a 1. Won't happen. We will have to treat all of these almost like we did here with this x and the c. They didn't match, we had to do chain rule. So let's do it, let's work through it. I'm going to take derivative with respect to t on the left side and derivative with respect to t on the right side. So let's just go through that. Okay, what is the derivative of c with respect to t? dc over dt. Equals. Now, I'm going to do derivative of each of these separately. The 500 is 0, right? We won't write it this time. But what is the derivative of 2x squared with respect to t? 4x, so that still happens, times now dx dt. Okay, so it's still the chain rule. The 2 came out, power came down, but then you take derivative of the x with respect to time, or t, sorry, it's going to be time later, and then you get the dx dt. So you see how that's different? All three of those derivatives are different because what we were differentiating with respect to was different in each one of those. Understand? Okay. With that said, let's now move into the related rates that apply to business. Keep in mind, though, as we move into this right here, don't lose sight of this. This is telling you the rate at which the C is changing. We'll say cost, okay? The rate at which the cost is changing with respect to T, and let's say T is time. So it's like, okay, time changes a little bit. How much does the cost change, right? Here, time changes a little bit. How much does the X change, right? This is going to give you that rate that it's changing. So don't look at this as like a fraction. A lot of people look at fractions like 3/4, right? It's a fraction. The 3 and the 4 are separate. When you see dx over dt, think about it as one big clump together. It's not a fraction. It's actually represents the instantaneous rate of change in x with respect to t. How fast x changes if t changes a little bit. Okay. All right, I hope that's enough for us to get going here. So I'm going to put a word problem up here. This is going to look very much like what you're going to see on the test, so you'll want to make sure that you pay attention and ask questions. And this is out of 11.6 in the book. here we go. Okay, so I'm going to put some things up here. We have a cost function. C is equal to 5,000 plus 2x. I have a revenue function of 10x minus 0.001x squared. And yeah, that should be good here. So just keep in mind, this is your cost equation. And this is your revenue equation. So these are given to you, okay? Those are given to you. And we're told that this is the cost is C, right? Revenue is R. This is obvious already, I already wrote that, but X here is the number of flash drives produced per 1 week. All right, so this company is manufacturing flash drives. You know what flash drives are for a computer? Plug in, storage, right? So you got these flash drives. X is the number of flash drives that are produced by this company in 1 week, right? So if you tell me how many flash drives were produced in a week, I can plug this in and I can get the cost and the revenue, right? Okay, any questions at that point? All right. So here's the actual question, right? I'll even state it so that you know. Question is, if the production level is increasing at a rate of 500 flash drives per week, when production level is 2,000 flash drives. This is going to be a lot of words. Flash drives, comma, find the rate of increase of the following three things. Part A, cost. Part B, revenue. And part C, profit. Okay. Let's make sure we just understand what's going on here, all right? Your company's producing X flash drives per week. It says if the production level is increasing at a rate of 500 flash drives per week, what they mean is, okay, let's say in 1 week you produced 1,000, but your production rate is increasing by 500 flash drives a week, then what should we expect in that next week your production level to be? 1,500, right? So it's saying that the number of flash drives we're producing is increasing, right? Increasing. Maybe we hired a better employee, we hired someone else, he's a hard worker, she's a hard worker, whatever. They're making more flash drives. So the number of flash drives we're able to produce a week is increasing at 500 flash drives per week. It says that the rate is increasing at 500 flash drives per week when exactly the production level is 2,000. So the way you look at that is, I said 1,000 a second ago, right? Let's change that. Let's say our production level right now is 2,000, right? That's how many we're making per week. And at that point that our production level is 2,000, it's going up by 500 per week. That's maybe when we hired the new employee, and now our production level is going up. Okay, so 2,000 is what we're producing per week, 500 is the rate at which it's increasing. We want to see how that affects the rate of change or the rate of increase of cost, revenue, and profit. Okay? Let's work through this one, and then we'll see if the next one goes a little smoother. What is this quantity right here? The rate of change increasing, production level is increasing. What is that? How can I represent that with some mathematical symbol? The production level is increasing at a rate of 500. It's okay, so when you see rate, you should be thinking derivative. Anytime you see rate, think derivative. So this 500, okay, this 500 is the rate at which something is changing with respect to something else, but we need to figure out which it is. So 500 is the rate at which what is increasing? The production level, right? Which variable was the production level? X. If you look back, I erased it. It was over there. But I said X was the number of flash drives produced, right? It was a production level per week. So this is the rate that X is changing with respect to what? Time, right? Per week. So I'm going to say this is dx dt. That's given to us. Does everyone, can you interpret that from the wording? The production level is X. It's increasing at a rate means derivative, of 500 flash drives per week. Maybe I should have circled the per week also, because the per week is where you get the time in there. Is that okay? All right. What is it that we're looking for? What are we trying to find? In part A, what are we trying to find? Let's make this part A. We're trying to find what? So be careful. We are not trying to find the cost at a specific value. What we're trying to find is the rate of increase of cost, right? So we want dc dt. This is what we want. We would like to know the rate at which the cost is changing with respect to time. Understand? Are you all able to interpret that from this wording? Okay, what about this 2,000? Where does that come into play? When the production level is 2,000 flash drives. So what was the variable? What was production level? What variable? It was X, right? And this doesn't have rate in it, does it? This is just saying when X is 2,000. So I'm going to put here when X is 2,000. Okay, so let's see if we can just really put our heads around this. We have the rate at which X changes with respect to time, right? We want to know the rate at which the cost is changing with respect to time, and we'd like to know that at exactly the moment that X is 2,000. Okay? This is all the information we need to do the problem. Now, we just need to get an equation. So we have several equations here. We're going to obviously work with the cost one, right? So I'm going to write the cost equation down. And now, I want to differentiate this equation. What should I differentiate it with respect to? Should I differentiate with respect to C, X, T? You want to use some other variable? T. Why T? Yeah, look, that's what we're working with here, right? We are working with this derivative with respect to t, this one with respect to t. So when we differentiate this equation, let's differentiate it with respect to t. All right? Let's do that. What would be the derivative with respect to t on the left, and then the derivative with respect to t on the right? So this is exactly what I did before I put this problem up on the board, right? This is exactly the same sort of thing. What is dc dt? What is derivative of c with respect to t? dc dt. That's exactly what it is, right? Equals, now, what's the derivative of 5,000? 0, right? What's the derivative of 2x? Be careful. 2 is going to come for the ride, right? Because it's attached. What is the derivative of x with respect to t? dx dt. That's it, right? So the 2 came along for the ride, right? And we're just taking the derivative of x. I know you want to say that the derivative of x is 1. I know that part of you wants to say that. But you're differentiating with respect to time. So the derivative of x is actually dx dt. I'll tell you a story that might help stress how important this is, all right? I'm going to mute my microphone because I'm not quite sure this is appropriate. But remind me to unmute this, okay? differentiating, my mic's back on, okay. So when you're differentiating, the derivative of x with respect to t is dx dt, not 1. All right? Okay. Let's continue.
Would it be like that with all variables, not just x, right? So if like say x we're changing to like p or something.
Like p, it'd be dp dt.
No matter what.
No matter what. And it's actually amazing that mathematics works this way, because you can take any equation you've ever seen in your life. I don't know, have you ever seen that one before? Chemistry? It's ideal gas law. So if I take the derivative of this with respect to time, this is pressure times volume equals some constant, Avogadro's numbers. No, it's not. It's some other, there are two constants in here, and that's temperature. So this is a big constant, okay, so who cares? Pressure times volume, temperature. So we could differentiate this with respect to time. And so the derivative of this with respect to time would be d capital T over d little t. And then over here we would have to actually do a product rule and blah, blah, blah. But you can do it with any equation at all, right? Now with this problem, we come to this end result, right? This is what we come to at the end. And we're like, okay, well, what's the use of this? Well, let's go back and look at what we were actually trying to find. Look at this. We wanted to know what dc dt was, right? Well, that's what it is. It's equal to this. Twice this. Do we know dx dt? 500, right? So we can just rewrite this. dc dt is equal to 2 times 500, which is 1,000. Okay? Everyone see that? Now, what is that answer? What is it? 1,000 what? 1,000 flash drives? 1,000? What does that 1,000 represent? So let me help you see what that represents. So I'm going to write it up here. We have dc dt equals 1,000. The way you can figure out what this answer represents easily is by looking at these two variables and thinking about what they are. What is C? Cost. And cost is going to be in dollars, right? So this is going to be $1,000. And then per what? T is time, and we've been measuring things in weeks, haven't we? The problem is measured in weeks. So this is $1,000 per week. So let's try and wrap our heads around this. We had this company, we were producing 2,000 flash drives per week, right? That was our production level. We hired this new person, our production level is jumping by 500 flash drives per week, yes? What the result of that is that our costs are going to jump by $1,000 per week, okay? All right, next question is how is this going to impact our revenue? So we're going to run through the same scenario here that we did here, except we're going to use the revenue function instead of the cost function. With me? All right, let's do it. So for part B, what's funny is when I used to go to these clubs, this one particular club, they used to record the entire night, like all the music, and then like the DJ and everything would be recorded, and at the end of the night when you walked out, they'd just give you a CD. And it would be like the entire night, right? I still have that CD. Now I've burned it onto like a flash drive, and it's an MP3 form, but I'll put it on. It's funny. It's like brings back those memories, you know? All right, what am I going to put here for part B? Sorry, I'm getting all reminiscent up here. Okay, so for part B, let's write down what we're given and what we want, right? So what are we given? It's pretty much the same information, right? There's nothing new here. So we're given dx dt is 500. We want to know what what? dRdt is, right? That's what we want to know. And we want to know it at x is 2,000. Did anybody notice that in the problem we just did, that this x being 2,000 didn't come into play at all? Like in our answer, it never factored in, did it? It will factor in on this part B, you'll see. All right, so we've got what we're given. This is what we want to find. This is the production level we're at. And now the equation. So let's write our equation down. R equals 10x minus 0.001x squared. Now, what? We're going to do the derivative with respect to time on both sides. So we're going to go d dt on the left side. We're going to go d dt on the right side. Okay, so what is the derivative of the left side there? dr dt, right? And it's very nice for us to see that. Why is it nice that we're seeing that in this result? That's what we're looking for, right? Okay, so it's good to see it there. All right, now we need to take derivative of both of these separately. And I don't have a constant this time, right? So these both have derivatives. This is 10 times x. So how about we bring 10 down? And then what is the derivative of x? With club music in the background. What's the derivative of x? dx dt, right? This is dx dt. That's it? We're done here? Okay, what about this? What's the derivative of this? So you start out by just doing the chain rule, because you have a squared up there, you bring the 2 out, right? So it's the 2 is going to come out, it's going to hit this, we're going to get minus 0.002. When you multiply 0.001 times 2, you get this. Then x to the first power, right? I'm not going to put the power, but the power comes down. And then you have to take the derivative of this. That's chain rule. So what is the derivative of x? dx dt again. So that's the result right there. That's the equation we're going to work with. Are there any questions on that? This little chain rule, tricky little piece here, y'all are okay with that? All right, now we want to know what dr dt is, right? Good. Do we know dx dt? Yep. Do we know x? See how x appears this time? So we do know x is 2,000. And then dx dt is 500. So we have everything we need. Let's rewrite everything now. I'll put it right here. So we have dr dt equals 10 times x. Now x we said was 500. Dx dt was 500 minus 0.002 times x, which was 2,000, times dx dt, which was 500. So we might need to break our calculators out. Maybe not. The whole thing is 3,000? Okay, so we'll trust that you can get that. So it's 3,000 is dr dt. $3,000 what? So we look at the two variables. R is revenue. Revenue is money, right? So this is going to be dollars per week again. You can write it like this, or you can actually write the word per week if you'd like. Either way.
What if you did a slash and then per week? Would it be any different?
That'd be okay. But when you write the word per, it actually means slash. Yeah. All right, so what this kind of means is this. At a production level of 2,000, we hired the new person. Production level just jumped up by 500 flash drives. Our cost went up by how much? Our cost? 1,000. That was part A. Our revenue, though, jumped up by 3,000. So what about part B? Revenue minus cost. What do you think that answer is going to be? Profit is revenue minus cost. It should be 3,000 minus the 1,000, right? Which would be 2,000. Y'all buy that? So we can do that now. Part C. Part C is that, watch, let me write it down here. Profit equals revenue minus cost. Do y'all agree with that? I mean, that's the definition of profit. Yeah? So if I want to know for this one, I want to know how much the profit's changing, right? That's what I want. Take the derivative of this with respect to t. Right now, let's do it. Derivative with respect to t of profit equals derivative with respect to t of revenue minus cost. Okay, what is the derivative of profit with respect to time? dp dt. Okay, what is the derivative of revenue with respect to time? dr dt. Minus, what's the derivative of cost with respect to time? dc dt. See, this was part B, this was part A. That answer gives us part C. Yes? So this was $3,000 per week minus $1,000 per week, which equals $2,000 per week. Part C. Okay. Y'all want to do another one? Do you want to do another one? Do you want me to give you one and you do it? No? Yes? Yes? Okay. So let's try this. Let's do the same process, same question, okay? Well, actually, I'm going to change some things here. Change this to 1,500. Let's change this to 200 right there. And your cost equation is going to be 72,000 plus 60x. And your revenue equation is going to become 200x minus x squared over 30. Let me just warn you here, just quickly here, that this right here, x squared over 30, this, if I were you, I would look at that as 1/30 times x squared. It's a little bit easier to work with if you look at this as 1/30 times x squared, because when you do the derivative, the 2 just comes out. I think it's cleaner to work with. Think y'all can handle that? You want to work together on this? Yes? Yeah? Okay. All right, I'm going to let y'all go with it. I'm going to give y'all, we've got only about, 30 minutes? Let's see how long it takes you to do this. I did change some numbers here. This is 200 now. This is 200. And this is now 1,500. Those changed. And of course, your functions changed. Your cost and revenue functions changed. If you have any questions, let me know. I'll come by and check. Not muted. Okay, now. All right, for this next problem, this is a retail store. Has this equation here, S equals 50,000 minus 20,000 E raised to the negative 0.0004x, where S is weekly sales, and weekly sales in dollars, and X is your weekly advertising costs. In dollars. Can I erase the right side? Yeah. Okay. I'm going to write the question down here. If current advertising costs are $2,000. Do we want $2,000? Yeah, $2,000 per week. And they are increasing at a rate of $150 per week. Then what is rate of increase or decrease of sales per week? All right, there we go. Question mark. So this equation somehow gives us the money we're going to make, in sales at our store if we spend